So this next section is about locking, and with these two types, Mutexes and RwLocks, which is read-write locks. So let's look at that. So the most commonly used tool for sharing data between threads is a mutex, and that's why they exist, is because they can be used between threads. Mutex means mutual exclusion. The job of a mutex is to ensure threads have exclusive access to some data, and the way they do that is they temporarily block other threads that might be trying to access it at the same time. And so I guess they're pretty simple. A mutex only has two states, locked and unlocked. And when a thread locks an unlocked mutex, then it's marked as locked, and the thread can immediately continue. So you get a lock, you mark it as locked, and then you keep on going. Now, if you have an already locked mutex, and then a thread comes along and tries to lock it, then the operation will block, and that's something you need to be careful about with mutex. It can kind of just wait forever for access. The thread is put to sleep while it waits for it to be unlocked, and you can only unlock on a locked mutex, and should be done by the same thread. So you make it drop to unlock it, and if there are other threads that are waiting, then it'll cause if you unlock it, then the threads will be woken up, and then they can try to lock it themselves. So this is kind of interesting. Protecting data with a mutex is simply an agreement between all the threads that they will only access the data when they have the mutex locked, and that is what lets you not have data races in Rust. So that's for both types. And then getting into mutex. The Rust standard library uses this through standard sync mutex, and it's got this generic T here, which is the type of the data that the mutex is protecting. And by making this T part of the mutex, the data can only be accessed through the mutex, and that's the safe interface that it provides. And this is the probably the most interesting part of this section. So to ensure that a locked mutex can only be unlocked by the thread that unlocked it, some people might be wondering why, if there's a lock method, why isn't there an unlock method? And that's because you could pass it around, and then other threads could start, trying to unlock, and it would be really lead to all sorts of problems. So what you do instead is you have you lock, and it returns this mutex guard. And that's the guarantee. It's sort of like an exclusive reference through the deref mute trait, and the way that you unlock it is you just drop it, and that so that's the way it works instead of having a method to do it. And then when you drop it, it gives up its ability to access the data, and then other threads can have access to it. And so here is an example. Let's move to code right here and just type that out. So let's say first we bring it into scope. Why am I all caps? Use standard sync mutex. Do that, and then you can see there's a scoped thread here. Still fairly new in Rust. I think they've been around for about a year now. So you have the simple mutex, and then you go thread scope, and I think it's use standard. Standard sync thread. There we go. Then we have to give it a name. Hold on a second, I'm typing this wrong. Okay, there we go. Open that up, and you see in the examples they always call it just S for scope. It can be called anything. And for something without a name, 0 to 10, and this is where you open up your threads inside the scope here. Guard equals what do we call it? N.lock.unwrap. You do that, and then you've got this guard hanging around, and that gives you access, and then you do that and 0 to 100, and then use this deref into the value itself, and then you're allowed to change it like that. And then at the very end, you can put this assert eq in there, and it's not going to panic because it's going to equal. And this this into inner will take. Then we have to unwrap it because it might not work. And what is it going to be? 1,000. So into inner will just take out the value from inside the mutex. And then bring up the terminal, and then cargo run, and this should do nothing to show that we haven't panicked. There you go. So that was pretty easy. Let's get back to the book. Okay, so here we have a mutex of I32. It's protecting an integer. We spawn with 10 threads. Each thread will first lock them. The guard is implicitly dropped right after modifying it, so when the variable goes out of scope. So we don't, that's why you never see actually calling drop on the mutex. After that, you can safely remove the protection through into inner, takes ownership of the mutex, and then it gives the value itself back. And then, so even though the increments happen in steps of 1, you can see right there, a thread observing the integer would only see multiples of 100 since it can only look at the mutex when it is unlocked. And you can, so you can show it, there's a new line here, which is to clearly see the effect of the mutex, we can make each thread wait a second before unlocking the mutex. And this is going to make it take 10 seconds. So if you go to here, add this new line. Let's see, where are we going to put it? Right here. Sleep, and we're going to do time duration from seconds, like that. And then this is going to make it take 10 seconds. And you can see it's just kind of hanging out there for a while. So each thread only waits for 1 second, but the mutex ensures that only one thread at a time can do so. And so, so that's not parallelism. And the way you can make it parallel is you can, let's see, there we are. You add another line, and you can see right here, if you drop the guard and therefore unlock the mutex before sleeping 1 second, so you drop the guard here, then it'll happen parallel. So there's no, nobody has to wait around for the guard to be dropped. Instead of dropping here, you drop before you go to sleep, and then it's going to only take 1 second to work. So let's put that line in. So all you have to do is drop it right there, drop the guard, and then we pull up the terminal again, and then run it, and it should take 1,000, 2, there you go, a little bit over a second. So that is the point in this section. And with this change, the program only takes 1 second, since now the 10 threads can execute their 1 second sleep at the same time. And so, yeah, there you go. That is the importance of keeping mutex locked as short as possible. And it's always more difficult if you have a more complicated, basically, if you have a lock and you're passing it around and you have to remember, is it still locked and are any threads trying to access it? So you want to keep the locks as short as possible.